Thank you very much for coming. Good afternoon. We had great pleasure to have Ron Sinton here. I assume that everyone knows who is Ron Sinton. And probably everyone almost in this room used the system. So Ron did his PhD in Stanford University. He's developed the solar cells that after that was still used by SunPower. He's one of the founders of SunPower. And then in '92, he established his company, Sinton Instruments, and changed the way that we measure lifetime or do characterization, at least in silicon solar cells. So all these terms like Suns-Voc, implied VOC, everything is Ron works, and I assume that all of you know how important is that for us. Ron also was here in Australia quite a lot of times in the 2000s, something
90s.
90s, late 90s. So he's quite familiar with Fuji Beach, and Baruza still knows him very well. So please welcome Ron, and I'm sure that we will have a great seminar.
Thank you, Zev. I'm really happy to be here again after 15 years since the last trip to Australia. And today I'm going to talk about implementation of advanced solar cell analysis at cell test. And I'm really pleased to talk about this topic. It's been a lot of fun to develop a new tool. And I have to say that it's been a lot of work for the co-authors, which are my engineers, my 5 engineers at Sinton Instruments. And so just to give you a frame, around 2000, I presented this table, which was my concept for process control in a silicon manufacturing line. And you could see that electronic process monitoring, you could start with the incoming wafers and then end at the front metal and anneal. And this was primarily lifetime testing, sheet row testing, and you could start measuring voltage as soon as you had a phosphorus diffusion using the Suns-Voc method. This is kind of an updated graph of this, and we've extended it back to the feedstock and into the system as well. And it shouldn't surprise any of you that my favorite electronic monitor is to measure lifetime versus carrier density. And so what we've done, what our concept is to have a consistent framework all the way from the feedstock into the system of measuring the same parameters so that you can optimize each step individually. And what's been really important in my experience is to frame all the results with the same terminology so that someone who is working on crystallization can discuss parameters with someone working at the system level, because there's been a bit of a disconnect historically from where the terminology comes from. And so just to give you some examples of the extremes here, this is how you measure the feedstock quality. If you have polysilicon, what they do is they grow this tiny little float zone boule, and then they measure its lifetime. And this is kind of magic, because you can do this without any surface preparation. You just take this little float zone boule and measure it, and you get a lifetime which you can measure 7 milliseconds as here, or up to 20 milliseconds on these little float zone boules. So this tells you that the chemical composition of the feedstock meets a certain standard. Then at the other end, this is my solar array, and you can do the Suns-Voc curve, which we often do for solar cells or precursors, and you can do this on entire systems. And the way you do this is kind of interesting, and that's that you open circuit your array in the middle of the night, and then as the sun comes up, or before the sun comes up, you track the voltage as it increases from darkness until you have a blue sky. And at this point, the array is just looking at the blue sky, not the direct sunlight. And that puts you around the corner of the Suns-Voc curve. And then later in the day, when the inverter is running and you have the maximum power point, you can plot the maximum power point and correct it for temperature. And this gives you really good indications of the series resistance of your entire system. as well as any mismatch losses that you might have, because the Suns-Voc curve shows the ideal diode of your array without any mismatch losses. So this could be very valuable at the systems level. And you can see that it's the same physics all the way through. And that's our goal. But today, I'm going to talk about cell test specifically. And the reason we want to work on the cell test is that cell test is unique in a production line in that it is the only place in the line where 100% of the wafers are measured. It's been difficult putting lifetime testers in the line because it's a little peripheral, but every line has a cell tester that measures every wafer. And so we need to take the maximum advantage of this opportunity and do some device physics at cell test. And of course, we're going to measure, and I'll talk about in this talk, lifetime versus injection level, the relevant measurement of series resistance, which we use Suns-Voc. I'll talk about the time response of high efficiency cells, and I threw in a few extra slides after talking to Allison yesterday about this. And then some examples in the end. I'll talk kind of interchangeably about results from two of our tools. We have a laboratory cell tester that uses a multi-flash technology. And what it does is it measures both the full IV curve with all the conventional parameters and the Suns-Voc curve as well, which has all the pseudo parameters, lifetime versus injection level, lifetime, J0, all these things. And in particular, what our tool does that isn't commonly done is that we measure the substrate doping. So I'll be coming back to this time and time again because it's really a highlight. And then we have the same capability in a production cell tester. And as of now, we've installed about 300 megawatts of this in production to date. And this has all the same capabilities, but it goes really fast, up to 4,800 wafers per hour. So the methodology that we use in this IV tester is that we measure the IV parameters with a multi-flash or a single flash technology, as I said, under filtered xenon lamp to be class A. We measure the substrate doping with the time-dependent continuity equation. It's basically just accounting. We measure the lifetime versus excess carrier density from the Suns-Voc curve, RS from the Suns-Voc and the IV curve. The shunt in the dark, we use a good data acquisition system, basically temperature with RTD and capacitance effects I'll go into some detail on. So I'll start with what I know most people here are familiar with, and that's the lifetime tester, which you do on test wafers before the at many steps in the process, but especially after the diffusion and after the PECVD nitride. And so you get this curve shown here, which is 1 over tau versus carrier density, and also lifetime versus carrier density. But at the IV tester, you get IV curves. And I've shown 4 typical IV curves here that I'll come back to time and time again in this presentation. We have a typical aluminum back surface field cell, a PERC cell, an example of an N-type cell, and then we have the Auger limit here. But what you have to realize is that these are the same thing, the lifetime curves and the IV curves. And I illustrate this here. Up here we have the little schematic of lifetime versus carrier density. And so if you have a list of carrier densities, you can take a carrier density, calculate the lifetime, and use this to calculate recombination. And the terminal current is just going to be the photo generation minus the recombination. So for every delta N, it implies a current density from a solar cell measurement. But similarly, if you take the delta N, you know the voltage because you can calculate the log of the PN product over Ni squared. And so the only additional parameter you need here is the substrate doping. And you get IV curves. So this is going from lifetime to IV curves, but you can do exactly the same thing to go from IV curves back to lifetime. To show it in a little more detail, here's the voltage equation, but the current is the photogeneration minus the bulk recombination, the J naught front plus J naught back times the NP product over Ni squared. And these are all the parameters that you would be measuring at the lifetime tester in the process. So first, I'll show how we get these series resistance and shunt resistance parameters using an IV tester. The shunt resistance can be done in two ways. Here I show that it's just the slope of the IV curve at the short circuit current. We also measure just the slope in the dark of the IV curve at 0 volts with an ohm meter. The RS at the operating point we get by comparing the Suns-Voc curve with the IV point. And this is the best way to measure RS because it is the one that's relevant for power loss at the maximum power point. So next I'll talk a little bit about time response in high capacitance cells because this is becoming more and more an issue in the industry. And the problem here, I show in this little inset how a typical tester works. And this is per cell on a cell tester or per cell on a module. And what you do is you start a flash and you have a constant light pulse and you ramp the voltage from short circuit to open circuit. And I show the IV curves that you would trace using this method if you ramped it in 2 milliseconds, 5, 10, 20, 100, and then steady state is this outermost curve. And you can see that you underestimate the efficiency of a high capacitance cell. This one that I modeled was 720 millivolt N-type wafer, 200 microns thick, which was kind of industry standard when I did this graph. So this, you can see that even for a 100 millisecond pulse, you have a very significant error in reporting the maximum power. And the reason for this is that the new cells have very high capacitance. And it's not a small effect, it's a huge effect. And so I plotted here the capacitance, which I'm defining as the change in charge per change in voltage for a aluminum BSF cell, which is P-type 1 ohm centimeter. And then the PERC cell, you can see that we've increased the capacitance by a factor of 20 in just going from aluminum BSF to a PERC cell. So it's going to have a time response 20 times slower. And then if you switch to N-type material and very high maximum power voltages on the lower curve, then you can have 200 times the capacitance of an aluminum back surface field cell. So you can see kind of the crisis here is that you have 50 gigawatts of installed production with module testers that are optimized for this type of solar cell. And now you're starting to build solar cells that are 200 times slower in time response. So the way we deal with this is actually very simple in that I've shown you these equations. And what you can notice is that you would hold the carrier densities constant on the right, which is the charge in a solar cell, if you just hold V plus J R sub S, the terminal voltage plus the series resistance voltage loss constant. And so we just do this, and it's quite simple in concept. And what you're actually doing is testing under constant charge conditions. And you measure the voltage and the current while holding the voltage plus JR sub S constant using a feedback circuit. So we have the hardware do all the work in order to get an accurate measurement. And I didn't have a PowerPoint, but I have a PDF of a paper. So I'll just show a few extra slides here. to illustrate this. And if you see the current density on the left axis and the illumination intensity on the right axis, the red plot is the light intensity versus time. If you had a 1 millisecond half sine wave, this would be a very fast flash. And what you should notice is that the blue is the current that you would get out of this solar cell as a function of time with this 1 millisecond flash. And you can see that at every light intensity, the blue line, the current, is phase delayed from the light. So on the rise time, you would have a much lower current at the same light intensity as on the falling side of the light intensity, where you would get a much higher current. And in black, we show the steady state current. And of course, it behaves as you would want it to. It follows the light intensity precisely, totally in phase. And so you would get the black curve if you did this half sine wave over 10 seconds instead of 1 millisecond. So the trick is, by using this constant V minus JR sub S, you actually modulate the voltage. And I show the voltage on the lower graph here. And instead of holding it constant at 0.6 volts, the maximum power point at the terminal, you actually modulate it in a certain way that the current density is in phase with the light when you get it perfect. And it's also perfectly overlays the steady state current that you would get at each light intensity. So what this means is that you've made your result, your measured result, independent of the details of the light transient response. And so I'll skip to the end here and show some results that we had a flash and its light intensity on the vertical axis and time on the horizontal axis. And you can see 3 different flash pulse shapes. A very short one, which we'll call about a millisecond, perhaps 2 milliseconds, and 5 milliseconds. And when you take a power curve with these 3 flashes, you see that the short flash has an overshoot in the power. It has quite a big error. And the medium and then the full one are also a little bit different. If you use the trick of voltage modulation, all 3 of the curves lie on top of each other, validating that the method works very well. And if you plot this in terms of error in power measurement on the vertical axis for the short, medium, and for the long, medium, and short pulse, you can see that if you had held the voltage constant, you have an error of up to 15% for the short pulse that can be totally eliminated using this little trick. And so this trick was novel in 2006 when I presented this paper, but now you'd have to call it the conventional method in the sense that all of the modules that have been tested, over 20%, so about 6 gigawatts of modules, have been tested using this technique. So it really is the incumbent technology for high efficiency cells. So back to the PowerPoint. So I'll show an example of data from this flash tester. And I'll start with the high efficiency N-type cell, shown in orange here. And this is, in blue are the IV points. In red is the Suns-Voc curve. And then you see the maximum power point there. And so you can use the Suns-Voc curve to construct all your lifetime data, as I showed in a previous slide. And you get the typical 1 over tau versus carrier density with a linear slope for N-type high-efficiency cells, where the slope gives you the sum of the J0 back and the J0 front. And if you take the intercept at the negative doping, then you get the bulk lifetime as well. And so these are very, very good to get. So on this particular cell tester, you get all of the conventional parameters, which I show on the left. And then you get all of these pseudo parameters as well. And there are so many of them, I highlighted the key ones in red, which is the pseudo-fill factor, the pseudo-efficiency, the J0 of the emitter, the estimated bulk lifetime, and then finally the doping. So the next example I'll give is a PERC cell. And this is the IV curve and the Suns-Voc curve. And you can see it's a typical PERC cell with about 660 millivolts open circuit voltage. The lifetime curves are a bit different here because you're in low injection, so you can't get the linear slope region of the lifetime curve where you can extract out the J0 and the bulk with precision and uniquely. So you get this rather flat injection dependence, and then you have the injection, you have a very low lifetime at low carrier density. And this is typical for any p-type material because of the boron-oxygen defect or boron-iron or many other reasons. And so we actually did a study on this, and it was presented at the IEEE by Adrian Blum. And I'll show some slides for this. And what this study was is that we got different vendors to give us batches, 5 different types of batches of solar cells. The first was the aluminum back surface field cells. We also got aluminum BSF cells on high performance multi. We got some multicrystalline PERC cells, some monocrystalline PERC cells, and some high performance monocrystalline PERC cells. And so what we're going to look at is the substrate doping versus lifetime, and lifetime versus delta N at the cell level. And the reason you might want to do this is because the substrate doping can give you a proxy of where the wafer came from in the ingot and the brick. So you can reconstruct the ingot or brick position in a sense without having to track it with an ID all the way through the process. And this can give you a proxy for the oxygen level because you know that there's more oxygen in the seed high resistivity side of the ingot. It could give you a prediction of the LID behavior. It also gives you information relevant to lateral series resistance in the case of PERC cells. It gives the final substrate doping, which includes the changes due to high temperature steps. In most material, you have oxygen donors before you process the wafer, and then if there's a high temperature step, you anneal the donors and the resistivity changes. And so your device physics can be totally different at the end of the process than at the beginning. You also get the effective lifetime, which tells you about surface passivation quality, substrate quality, and contamination during the high temperature processing. What we're going to do is analyze the pseudo-VMP and the efficiency dependence on substrate doping and effective lifetime. We have a huge range in parameters, which helps in any experiment. In pseudo-VMP, we range from 515 to 584 millivolts. The efficiency is from 16 to 21%. The lifetime from 5 to 100 microseconds. And the doping from 5E15 to 3E16. We had a really nice sample set here. So the first thing I'll show is the dependence of the pseudo-VMP on the tau doping product. And down here in this formula, you see that the voltage, the pseudo voltage when there's no current, so the pseudo-VMP depends on the doping lifetime product here. And you get a pretty straight line, a perfectly straight line when you plot the tau doping product versus the PMP. If you look at efficiency, it's more complicated. And the reason for this is that efficiency isn't only voltage. It also has current dependence and series resistance dependence, which, because we have different vendors and different technologies and different cell designs, it's much more scattered. So this is a good place to get your fundamental parameters here. And so what you see is that this isn't the whole story. It makes a lot of sense to break it out into lifetime VMP dependence and doping dependence. And so we'll talk about the special cases. First, let's look at the aluminum BSF, the high-performance aluminum BSF. And in this case, we had just one doping level, pretty much, and we can see that the entire efficiency dependence is due to lifetime variation. Then if you look at the aluminum BSF, we're using the entire ingot here, and being a conventional ingot, you get a wide variety of lifetimes due to different defects at different points in the crystal, as well as doping. So there's both a lifetime and a doping dependence. And so the most interesting case, I think, that's very illustrative is these high-performance PERC cells. And what's interesting here is that you have a subset that has a fixed pseudo-VMP, almost independent of lifetime and doping. But you notice the symmetry here, that the higher doped wafers have the lowest lifetime. So they're a reflection of each other. And so if you come down to the formula, you see that that's exactly the case you would get if you had a very high lifetime, so that this term didn't matter. And you have a doping tau product which is constant because the J0 term is constant. So this is telling you that you're limited by J0. And this is very interesting because I showed you in the lifetime versus injection level curve, you couldn't separate out the J0 and the lifetime. But when you have a large sample set with variations in doping, then you have an experiment that clearly indicates what your voltage limit is due to the emitter saturation current density. So this gives you an indication of how you could use all of these detailed parameters in a production line with large data sets. I'll just make this more explicit. Suppose that you measured 200,000 multicrystalline cells, which is only 2 days of data on a production line for a tester. And your resistivity varied from 1 to 3 ohm centimeters. Well, you could take the 10,000 wafers closest to 1 ohm centimeter and the 10,000 wafers closest to 2 ohm centimeters and do histograms of those. And within each histogram, it would be independent of doping. But between the histograms, you would see the doping dependence. So when you start to get big sets of data, you can analyze it in ways that gives you a lot more information. It is really fun to look at millions of solar cells with this detail of 30-some parameters coming out. So the last example, I took some slides from a presentation by Dave Smith at the IEEE. And what they presented were some 25.2% N-type full area solar cells. And they had used these to make a 24.1% module. But what's really interesting is that they did a full energy loss analysis in this paper, which they showed here, varying the biggest loss being rear optical loss, and then bulk lifetime front reflectance on down to Auger and radiative recombination. And I'll show how you could measure each of these at the IV tester to the extent that you can. So first, bulk lifetime comes right out of the analysis. It's a parameter that's reported. You report the sum of the J0 of the front and the back. The RS that is reported from the tester is actually the sum of internal RS, grid RS, and lateral transport losses, kind of 2D, 3D effects. The Auger and the radiative, if you've measured the doping and you know the maximum power voltage, you simply calculate those. And they showed in this paper that by using an aperture and looking at the current density that they get from the middle of the cell versus the perimeter, they could separate out the edge losses. So they looked at more detail in the bulk lifetime because this was perhaps the biggest avoidable loss. And they were very interested in this because they because they track a baseline of test wafers, and they had data for months which showed that the 4 recombination regions on the surfaces each had these parameters, which when weighted by area should have meant that they have a bulk lifetime of 20 milliseconds. But on these record cells, at the cell test level, they're measuring 6.7 milliseconds, not 20. And so they went back and they looked at their test wafer experiment, and they decided that they needed to do the patterning and see what that did. And when they did the patterning, in addition to just having the large areas, then they came up with an answer that's consistent with the 7 milliseconds that they are measuring at the cell level. So by doing this comparison of the lifetime right before it's a solar cell and then right after, they could assess how much they're losing in the particular process steps that they're doing. So this is kind of the final result, is that I've coded in red the losses that you can measure directly at IV test, and the blue, which you'd want to do in an independent way, probably with a spectral response and a model to get the optical type losses. So in conclusion, I made the case, hopefully, that you can do advanced device physics at cell test. You get the normal IV parameters and the Suns-Voc, lifetime versus delta N, series resistant, shunt, and substrate doping. It enables a sophisticated loss analysis wafer by wafer at cell test. It's been fully implemented in line speed production tools, so you can get all of this data at a rate of 120,000 wafers per day per tool. Big data enables resolutions of parameters that were previously inaccessible. When you're in the lab, you have just a few wafers. When you're on the production line, you have millions of wafers, and you can really do fine analysis at a much more detailed level due to the big data sets. And so what we've done is shown that you can extend the well-known device physics tools that we've been used to using for 20 years to the cell test. And what we hope will come out of this is that in addition to being able to look back in the line and do diagnosis of what went wrong and tune up the line, you'll have a very detailed ID of each wafer at cell IV test right before it goes into the module. So you can also use all these characteristics to try and correlate with reliability issues, like the LID from oxygen, the LETID, whatever. And so we're very interested to do some studies and collaborations and see if this gives you some better physical insight into the module stability and reliability of actual systems. Thank you very much.
Thank you very much, Ron. Questions?
There have to be some questions. Yes?
Thank you.
Very interesting, very nice talk, really. With the measurement method you showed with the basic flashlight and you modulate the voltage, could you actually use just the onset and extrapolate if the capacitance of the cell is known to make the process significantly faster?
Use the onset. I don't
Yeah, because you showed the complete flash, right? And you got a phase shift with the current, and you compensate with that by modulating the voltage.
Yes.
If you know the capacitance of the cell, which you can measure by other means, right? You could actually just use the onset or actually a smaller flash, and calculate the efficiency this way, right? Which could save you time on a per test base.
So we're doing some of that sort of thing in order to do the production tester, where you don't have time to do multiple flashes. So that's exactly the strategy, is to get it all out of one flash, and you have to use a lot of these sorts of tricks to do that. Yes. Yeah.
Ron, I'm glad you mentioned the reliability stuff. I've seen some examples of that in some of the data that I've looked at, that there's some much better things that you can probably be watching to tell you something about reliability. You know, we've been a bit obsessed with just looking at power. How receptive have you found manufacturers to that idea that there's something else that they can be looking at?
We're just at the beginning of that. And so I'll just hypothesize here. I think that vertically integrated companies will be very receptive to this because they have control. And so they are willing to change parameters in the production line in order to improve their warranty claims. If a company is going to sell wafers, then perhaps they don't want to know. I don't know.
And if you sort of look at other manufacturing industries, all the analytics they do in other manufacturing is entirely geared towards understanding what their products can do when it's out there and how it's going to last.
Yeah, and I think you can.
And we don't do any of it yet, or very little.
Yeah, I think that the vertically integrated companies, the ones that sell power, do. So that's an interesting point. And the reliability is kind of driven by the bank, because the bank determines the finance rate for the system for 20 years based on the power production. And so it's an interesting model where the bank is determining the cost of a system based on the reliability. But that's the way where it is. And I think there's a huge opportunity for better physics and better predictive models. And it's a real problem in the industry because we want to keep innovating and bringing the price down, but the reliability issues make you extremely conservative because the bank will only finance what they have field data for, 2, 3, 5 years. So how do you introduce a new product? And so the more science that goes into the reliability studies, I think the better we can do at convincing potential customers that we have a new innovative product that will last 20 years. Surely I'm not this intimidating.
Ron, I also have another question. To the capacitance measurement, or like to avoid the capacitance in the IB measurement. Couldn't you just use the phase shift that comes directly out of the raising and falling arc of the flash data, and just say the phase shift is directly related to the capacitance and just do a mathematical fit to compensate?
Yes, but the capacitance is not a constant. It's a function of voltage. So it gets a little bit complicated. And also, on single cells, the electronics is very difficult to get right. It's very difficult to know phase shifts with a high degree of precision because you have time response of the intensity detectors, and you have phase delays in the hardware as well as the device under test. So we use a combination of things to try and minimize these errors. So you do want to take advantage of every shortcut you can get away with, but you can't get away with all of them.
For the extraction of the shunt resistance, you said you measure it at the gradient at voltage equals 0.
Yeah.
Have you looked at the errors that can arise from having like different J0 components, because they'll also have a non-zero component there?
Right. Once you get to high efficiency cells, you don't have that. And what we trust the most is a ohm meter measurement, which is to put 1 milliamp across a big cell and see what the voltage is in the dark. Rhett?
I've got one, Ron. I think you mentioned you got cell testers for 300 megawatts of production. That's a very small fraction of the current production levels. Why? Why so small?
Because we sold the first one a year ago. We're hoping for more.
On your RS extraction method, obviously there's a few ways that's done. Some are better than others. Have you done any work sort of comparing them or validating them on the bigger data sets for manufacturers? Because some of the stuff, I think, like when people use bad techniques, for instance, you can see it in the big data sets. You can see where there's errors in the way it parameterizes and stuff like that.
Yeah, well, the worst way you would do it is with a 1 diode or a 2 diode model, because that's not physical, especially, as everyone knows, for the boron, for p-type mono, where the curve shape is due to lifetime and not diode extraction. And so that tends to assign anything that would give a soft fill factor to be RS. And also the shunt and the J02 kind of trade off. So you just have a 6-parameter fit in that case, and in my opinion it doesn't necessarily mean anything. So the advantage of this is that you can clearly see the difference between a shunt and series resistance, because if the IV curve, if the Sun's VOC curve is flat, then there is no shunt. And the Sun's VOC curve is a perfect model for the diode characteristic. It's not the diode characteristic put into a fit with all the errors. So the study that you're talking about, we haven't done it, but Stefan Gluntz's group has, and so there's a good reference for that I can give you.
Yeah, it's good because if you can completely decouple that RS reliably from your voltage, then you can make a lot better inferences on what that RS means and stuff, and it's much more useful.
Yeah, I mean, this is power loss. When you try and figure out what it means, now that's something else, because it can be transport losses, carrier density gradients in the cell. It can be all sorts of things that aren't related to the electric field.
More questions? So let's thank Ron again for great talk.